So now we have these two ideas of a subset of vectors spanning a vector space and being linearly independent. And this definition at the top puts them both together. So now we have the same setting. We have a vector space, we have a field. S is a subset. What we're defining is S being a basis for V. So S is a basis for V over the field F if it spans and is linearly independent. Okay, so what that means is every vector of V can be written as a linear combination of those vectors from S. So let's say I'm thinking of S as the set V1, V2, dot, dot, dot. Okay, so it can be written as a linear combination of vectors from S. So maybe an A1, V1, A2, V2, dot, 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 all the way up to some list AN, VN. And moreover, it has to be linearly independent. So the only solution to A1, V1 plus dot, 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 all the way up to AN, VN equal to 0 is if A1 and A1 and A2 and A3 and all of them up to AN are 0. It's that trivial solution. All right, so one thing I forgot to point out in the last video, and we'll see going forward, is when I write that A1, V1 up to AN, VN equals 0, that 0 is really a 0 vector, and it depends on what setting you're in, what V is. It might be the number 0 in some, it might be the 0 matrix, it might be, if you're in R2, it might be the vector 0, 0. And so there's some interpretation there that you have to do. The 0 down here, though, the AN1 equals A2 dot 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 equals 0, that's 0 the number, because F is our field of scalars. All right, so a basis is a spanning set and linearly independent. So now we have a couple results that tell us how important a basis is. So if V is an F vector space and we have V1 up to Vn, that's a basis for V, then every basis of V has exactly that same number of elements in it. And what we call that number is the dimension of the vector space. So if the vector space has n elements in a basis, it's an n-dimensional vector space. Okay, if we're going to see some infinite vector spaces, so if we have an infinite vector space, it means there's going to be an infinite basis. Okay, so let's look at some examples. So 1 root 2 is a basis for Q root 2 over Q. So we saw that that was a spanning set, and we've seen that it's linearly independent, that the only way to write A plus B root 2 is 0 is when A is 0 and B is 0. Okay. Similarly, we could do something like 1, I'll leave that blank for a second. We'll come back and fill it in. What's a basis for, say, Q adjoin root 13 over Q? So if we wanted to write anything from anything from Q adjoin root 13, we would need as basis elements 1 and the square root of 13. So all the elements there look like A plus B root 13. All right, let's think about a basis for Q adjoin 2 to the 1/3. So we've dealt with this a couple of times now, and if you remember, the elements here looked like A plus B times 2 to the 1/3 plus C times 2 to the 2/3. And so that should give you the idea of our basis. It's going to be 1 for that rational term. Then we need a 2 to the 1/3 term and a 2 to the 2/3 term. Okay, and so what we're saying here is these were 2-dimensional, and this guy is a 3-dimensional vector space. And let's do a 4-dimensional vector space. So 1, root 2, root 3, root 6 was our basis. It was both spanning and linearly independent. For Q, adjoin root 2, root 3 over Q. Okay, and so that space, Q adjoin root 2, root 3, that's a 4-dimensional space. All right, let's see some different ones than we've dealt with before. So how about Rx is an R vector space? So let's talk about what a basis would look like here. So elements, these were the ring, this was the ring of all polynomials with variable x. And so they looked like there was a constant term, a linear term, a square, x squared term. At some point, they ended with whatever the degree of the polynomial was. Here I've written it as n. Okay, but n can be any element of z. So any positive integer. And I think instead of positive, I better be more specific here because it can be 0. So let's call it non-negative integer. Okay. So what this means is I know what these generic elements look like, and so I can take a stab at writing down my basis because I need a linear term. So that a0 is times a 1. I need the x term. I need an x squared term all the way. I need an xn, but now here's where things get a little bit weird because I can have a polynomial whose degree is 100. It would end with x to the 100. I can have one whose degree is 5 million. It would end with x to the 5 million. And so this basis doesn't stop at xn because n can be anything. So it continues on forever. So this is an infinite basis. And I haven't convinced us yet that it's a basis. I definitely think I talked through the fact that it's a spanning set because we said any element can be written like this. And so I know if I allow every power of x, I can write down any polynomial that I want to. But we didn't talk about why it's linearly independent. And if to do that, we need to think about of that. So we need to think about how can we solve a0 plus a1x plus dot 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 plus anx to the n equal to 0. All right, and by saying how can we solve this, what I mean when I say solve it is make these two polynomials the same. Not solve for x, but make these two polynomials the same. Okay, so I'm not looking for, oh, x equals 5 is the solution to that. I'm looking for, how do I make this polynomial that's an nth degree actually be the 0 polynomial? And so that's the tricky thing here, is what we mean by that 0 is the 0 polynomial. Okay, and so our answer to this question is it linearly independent? How can we solve this? Is the only solution, if it's going to be the 0 polynomial, that means that all the coefficients are 0. A1 is 0, sorry, A0 is 0, A1 is 0, all the way up to 0. So are linearly independent. All right, so this was an infinite dimensional vector space. Okay, let's do one more. All right, let's do 2 by 2 matrices with real number coefficients. So this is a vector space over R, all real numbers. Okay, elements here look like A, B, C, D. So they're 2 by 2 matrices with real number coefficients. A, B, C, and D are all real numbers. And so I want to be able to take A, B, C, D and write it as a linear combination of some specific vectors. And again, the goal here is these are my scalars, which means they're from R. And then I want to put a dot, dot, dot there at the end. These are vectors, and they're the 2 by 2 matrices. That's what we mean by vectors in this situation. And so like we saw before, sometimes this is pretty easy to do. I mean, I have some real numbers to play with, right? My scalars could just be A, B, C, and D, because remember, they're in R, right? So I'm going to try to just use those as my scalars. So I take A, B, C, D, and I want this to be A times something. And then that becomes pretty straightforward. If I want A times something and I want an A in the upper left, I just put only a 1 in the upper left. B times the only one I'm going to put is in the upper right, everything else 0. C times 0, 0, 1, 0, and D times 0, 0, 0, 1. Okay, so the set that I'm talking about now as my basis is those 4 vectors. All right. So now, one more question here is, are these independent? So are these linearly independent? If I have an expression like the one up above, A times 1, 0, 0, 0, B 0, 1, 0, 0, C 0, 0, 1, 0, D 0, 0, 0, 1. If I made that into 0, and here making that 0 means making it the 0 matrix, what's the solution here? And you should see up above that expression, up above we said was just equal to A, B, C, D. We've already seen that. And so I want A to be 0, and B to be 0, and C to be 0, and D to be 0. That's the only solution. And so this guy right here is a basis for M2R over R. And so that means that this vector space, M2R, is 4-dimensional.